Hello, geometry students. Mr. Figuet here, and we are going to talk about geometric proofs, and we are going to begin at the very beginning. So at this point, you have hopefully talked about the structure of a two-column proof, and we've looked at some algebraic examples so that we can start with a math topic you are strong and familiar with and show you the structure. This video is going to talk specifically about how we can apply geometric concepts. So the first thing I want to take note here is this concept of deductive reasoning. So the idea of deductive reasoning is the idea of chaining together various definitions, postulates, properties, and theorems together to build brand new facts. Essentially, what we're doing is taking a bunch of if-then statements and chaining them together. So like here's an example. So if I have a triangle is equilateral, we can conclude, so if a triangle is equilateral, we know then that the three angles and the three sides are going to be equal. Now, here's how we can chain together another if-then statement. A triangle, if a shape is a triangle, what can we conclude about that as well? Well, we can conclude that the three angles add up to 180. So we've taken two various mathematical facts, the fact that if a triangle is equilateral, then specifically we're going to talk about the angles being equal, and we also know that three angles add up to 180. And so we can take both of these statements. Now, if we know if a triangle has three equal angles and if a triangle adds up to 180, we can conclude that an equilateral triangle has three 60-degree angles. So this is a concept that we chain together and we use a lot. And all we're doing in this video is we are going to formalize this concept in looking at various definitions, postulates, properties, and theorems that we've learned. So I'm going to go through these three examples first, and then we'll have an opportunity for you to try batches of this on your own. So one of the first facts here that we have is we have we do have two shapes here, but we have two triangles. What is given in this first diagram is we are given triangle NKL and triangle LMK. That's all that was given to me. Now, the reason no measurements have been given to us is because there is one fact I can pull from this diagram, and I don't need any numbers to tell me that. And that is that the triangle NKL and the triangle LMK both share this side LK. And what we've learned in learning the reflexive property is that we can say that LK is congruent to LK. Again, this might seem, let's write this down, reflexive property. This might seem redundant, or it might seem silly that we actually have to write this out, but this will play an important role when we get to triangle congruence theorems in the last part of this lesson. Now, here's another property that we've also learned in the past, and it is called the substitution property. So I have a picture of some angles up here, and what I'm giving you as ironclad fact is that the measure of angle 1 is equal to the measure of angle 3, and also the measure of angle 3 is equal to the measure of angle 2. So this has all been given to me. Now, what I want to try to do is I want to create a new fact from this. And so the substitution property essentially says that since angle 3 is here and angle 3 is here, I can take anything that I see that is equal to angle 3, in particular angle 2, and substitute it into that first fact. So I'm taking the angle 3 out of it, and I'm putting the angle 2 in its place, creating a brand new statement that the measure of angle 1 is equal to the measure of angle 2. And what allows me to do that is the substitution property. So basically, whenever two equality statements have something in common, you can create a third equality statement. Some of you may be familiar with this as the transitive property. Now, for the last one here, specifically, we have a lot of things we can go with here. So the only given that they have in this situation is that AD is going to intersect EF. Now, there's a lot of places we can go with this, all right? And two of them in particular will be that we create then vertical angles and linear pairs. Depending on what your objective in a problem is, you will pick one over the other. For this case, I want to focus on vertical angles. So we can see here that angle ABF and angle EBD are considered vertical angles. And so one statement that I could write that would be true is that angle ABF, let's write that in the correct order, ABF is going to be congruent to angle EBD. And what allows me to say that is, once again, the vertical angles definition, the definition of a vertical angle. Now, if some of you looked at this and said, but wait a second, couldn't I say these two red angles are congruent? The answer to that is also yes. So we could have alternatively wrote ABE is congruent to angle FBD. And once again, that is going to be for the same vertical angle definition reason. Now, do you have to write both of these down whenever you see vertical angles appear? No. You're only going to write down what you need to help you get to your objective. All we're doing in this video is learning to recognize equality statements and equations we can build from geometric diagrams. So how the rest of this video is going to work is that I want to give you 4 of them to try at a time. So I have 4 different definitions that I want you to try to give me what the conclusion is. So number 1 is linear pairs, 2 is the midpoint definition, 3 is the angle bisector definition, and 4 is the segment bisector definition. What I would like you to do right now is to pause this video and try to see if you can write out a conclusion for each of these statements. So go ahead and take a pause now. All right, let's go through these one by one and see how we did. So for linear pairs, what we want to conclude here is that when linear pairs are present in a problem, which all we need to know is that a line and another line are intersecting, that the adjacent angles formed by those 2 lines will be linear pair, and more specifically, we know they add up to 180. So I created an equation that said that these 2 measures of these angles are going to add up to 180, and that's my linear pair definition. As for midpoint, when we're talking about B being at a midpoint, there's a lot of ways we can state this, all right? We know that AC is being cut in half, but the more important statement is looking for the equality, and that is that segment AB and segment BC are going to be equal to each other, or I use the congruent symbol for this instead. AB is congruent to BC. That's a definition of midpoint. We're not wrong to write this. There's nothing wrong with writing that, and you are allowed to. The only issue is it may not serve us a purpose when we get to triangle congruence. But it is a true statement and is a statement in other situations that might be warranted. Moving on to speaking of that, let's talk about angle bisectors. When a segment or array in this case is bisecting an angle, what it really is doing and what we want to focus on are what 2 equal parts are created. And so in this case, ADB and BDC are going to be congruent to each other. Could we write this down here? Well, we could write this, and this is actually not angle bisector. This would be the angle addition postulate, which I'm just going to abbreviate as AAP. And while this may be helpful, once again, in certain proofs outside of what we're learning in this unit, it doesn't really serve us much of a purpose when we're talking about triangle congruence. Remember, what we're trying to do is find things that are equivalent to one another. And then for the last one here, for segment bisector, we're looking for segment CD bisecting AB. Now, keep in mind that AB is the actual segment being bisected. CD is what's doing the cutting. So CD is not necessarily going to be cut into 2 equal parts, but AB is. And so in this case, I made a statement that AE, that's statement right there, and EB, which is right here, that those would be congruent segments. Now, that's just 4 examples. And so what I'm going to challenge you to do in the remainder of this your note sheet is to look at the next page. And I'm going to give you some hints, but then I'm going to send you off to work on these either by yourself or with a partner or in a group. And that is, I want you to utilize the definition of perpendicular when given this statement. What conclusion can you make? If I give you parallel lines like I do here, I want you to utilize corresponding angles and even same side interior angles to create statements. So I'm even going to add a 3rd line here because I actually want you to come up with 2 different conclusions, one using corresponding angles and one using same side interior angles in the diagram. Moving on to 7 and 8, once again, given parallel lines, this time I want you to focus on alternate interior angles. There may be multiple correct answers to this, so you can write those down if you'd like. Now, we've talked already a little about equilateral triangles, but if a triangle is equilateral, I want you to think about what statements you could write. There may be more than one way to write this. Feel free to write as many of them out as you want, and then we can discuss them back as a class. And then last but not least, focusing on 9 and 10, I want you to think about the fact that this is telling you something specific about this triangle over here. And I want you to think about what conclusions you could make. Vice versa, in number 10, I'm telling you straight up that the triangle is isosceles. I want you to think of some conclusions that you can write down here. Once again, for a lot of these, there are going to be multiple correct answers, multiple correct conclusions, but I want you to place an extra emphasis on looking for what segments or angles would be specifically congruent based on the information given. So that's my challenge to you, is to try these remaining 6 problems and see how you do with them. And then we will go over them as a class and we will review them together. That'll conclude this mini lesson. So I hope you have a great rest of your day, everyone.